I know it's been a while since I've made some videos, but I'm back. Had to do a few things. So I actually this video I want it to be mainly about equivalence in resistance between series and parallel. But before I do that, I actually want to go over just a general idea. Okay, so remember our battery. So let's make a circuit with multiple batteries. Okay, so let's just say each little battery is 3 volts. Okay, remember positive side up here, negative side down here. So I have three 3-volt batteries. Hopefully that's clear. Maybe let's make it 3 4-volt batteries. Hopefully that makes things clear. And then I just have again a circuit with no resistors. Generally you don't want to do that, but let's have that situation. Okay, when I add these batteries together, if this is 3 volts, 3 volts, 3 volts, and 3 volts all together, that's going to be 12. All of them kind of stacked on top of each other. Think of every volt in this situation, or every battery, like a building, but instead of think of every battery here like a building, just kind of stacking them on top of each other, and each battery is 3 stories. So if you had one 3-story building, another 3-story building, another one, and then one on top of that. So one thing I want you to remember is that when you measure voltage, you have to measure the difference in potential, okay? Because that's what that is. That's the difference in potential. So think of the electric way as in this physical way. I cannot, if I were to measure the distance in potential of some gravitational thing, think of potential energy again. What's the difference in potential energy if I got this point and the same point right below? Is there any difference in potential energy right there? No, there would be no difference in potential. So when you measure voltage, you have to measure between 2 different locations. So if I measure in the same location, the difference in potential is going to be 0. If I measure between the beginning of this building and here, then it'll be 3 stories, right? So same thing between one battery to the beginning of the other, it'll be 3 volts. If I measure from here to here, it would be 2 3-volt batteries, so it'll be 6 stories here. And then from here to here, it will be 6 volts. From here to here, 9 stories. From here to here, 9 volts. And then of course from the top to the bottom would be 12 stories and 12 volts. So that's what voltage is. It's the difference in potential. Hopefully that kind of makes sense to you. And something else, let's add something else. Let's just say I have 2 resistors in this. And then I have another one right here. Okay? As the charge is moving through, here, let me get right. As the charge is moving through here, it needs to use this potential that it has from the battery all the way to the bottom. Okay, so remember, think of it having a potential of 12 volts up here and then 0 down here. So think of 12 stories up here, or 12 volts, and then 0 volts. So as it's kind of going through the wire, think that there is no change in potential. Technically that's not true, but let's just assume that's the way it is. And then it doesn't matter. Let's just assume that these are the same size. So let's just say 5 ohms, 5 ohms. Okay, it doesn't really matter. So this is the vertical direction along this gravitational example. So we have to have the potential is lost here after going through the resistor. Do you kind of see that? And then the current flows through here, and then we have this wire right here. Again, the wire, pretend there is no potential loss through the wire. And then we have to go through this other resistor right here. And then is there another resistor after this? No, there is no other resistor. That's it by itself. So the potential that this circuit has at the beginning has to be used up with whatever material is in the circuit. So if I only have two resistors, then the voltage, the potential lost or dropped through both of them has to equal the voltage produced at the beginning. Again, just like you drop a rock in the at the top of a cliff, it's going to have to fall. And then that's my wire. If I only had one resistor, if this was gone, then I would forget about this and I would have to extend this resistor all the way down. What I'm just trying to say is that, again, this, however many batteries you have or the power source, that's the height at which this wants to fall, okay? And then the resistors are what is going to allow that charge to kind of drop, okay? And then the bigger the voltage is here, the more this is going to want to drop. So let's just say the bigger this is, the more the current wants to go down towards the bottom. Hopefully that kind of conveys some information. And by the way, both of these, since they are the same size, in this situation, I would just say this is 6 volts and 6 volts here. So if I were to measure, remember the difference, okay? I cannot measure a resistor in the same location. I cannot measure this here and here at the same place. I have to measure before the resistor and after. Do you see that? So if I were to measure this, the voltage of this resistor, I'd have to measure right here at the beginning and right here at the end. Now technically there's positive and negatives, but right now we're just gonna assume the voltage is an absolute value because that's the main idea I want to do right now. The signs we can worry about later. But again, if I have two resistors of equal size, then they're both gonna drop 6 stories or 6 volts. So I have to measure across from here to here. And once I do that, I would read 6 volts. And then if I measure from here to here, I would measure 6 again. What if I measured from here to here? What would I get? Well, if I measured here and at the end of here, that would be 12 volts, which again, the sum of the voltage dropped between the resistors in series should equal the voltage of the power source, the battery or anything else that you have right there. Actually, right before I move on to equivalent resistance, I want to go over one more thing. So for potential difference, or to measure the voltage, you have to measure from one point to another. With current, it is the exact opposite. With current, it's like having a speed gun, right? To see how fast something goes. You don't necessarily need one here and one here for the speed gun. For the current, you can just have one gun right here, just one little sensor to notice everything whizzing by. So that's the big difference, is when you measure voltage, you need, okay, I need a before and an after. And it doesn't matter, I could do here and here, or I could do here and here. So that's what I can do. With the current, I can just have one little sensor and it measures everything. Now, in this situation, how many paths are there where the current can flow through? Think about that. If I have just one river, the current is going to stay the same wherever you are. And if I add some obstacles, then it'll slow down the beginning and end. Think of like a leaky faucet. If I close it, then it'll only be able to move a little bit at a time. So the resistors limit the current, of course. But however, since this is only there's only one path, there's only one direction, then the bottleneck that is started by both of these, or caused by both of them, will distribute throughout the whole circuit. So even though the current right here has not met a resistor, it is, think of it again, because these electrons, there's 10 to the 20s of them, 10 to the 21, 10 to the 22 number of electrons flowing through this circuit per second. So they're constantly bumping into one another. So even though this technically has not gone through a resistor yet, it is behind these that are going through that resistor, which are behind these that are going through this resistor, which are behind these. So since there is only one way to go, there's no other path. The current stays the same throughout the whole circuit if there's only one path. that is very, very important to understand what we're going to find out next.